Time for us to get started. How are we doing? Happy Tuesday. Hopefully we saw that I posted the new assignment that'll be due a week from tomorrow. That's dealing with the algorithm that we started talking about yesterday. And let me just relaunch this. I wanted to go through another example of this real quick, because from talking to a few people yesterday, it seemed like everyone had a different but still a misunderstanding about how this was calculated or how this was done. So I wanted to make sure that
I'm gonna be okay. I'm gonna be completely honest. I think there's something somebody missed.
so I would like to do something about the same size and give people a little bit of time to work on it or ask questions about clarifying how to calculate it and then go through it. So let's just dive into it. We're going to need a row and a column that are going to be our initial values. We're going to use these exact same values. So we have a 0, a -2, a -4, -6, -8, and -10. We'll have a -2, -4, -6, -8, and -10. The question is, what sequences do we want to use? Let's choose a couple of sequences, and it has no bearing how similar those are to finding an optimal sequence. So we can just use A's, C's, G's, and T's. Anyone want to give me a 5-character string?
A, B, T, T.
A, G, T, what was the rest?
A, G, T, T, A.
Agata. Great. I need another one.
A, G, A, G, A.
Aga. I like it. You can take from that what you will. Something about computer scientists, I'm sure there's a good joke in there somewhere.
Clearly, it's Lady Gaga.
Lady Gaga, there we go.
It's serious.
All right, so let's dive into this. So there's our table. Hopefully the setup makes sense. How do we get started? Anyone want to walk me through the very first calculation? I'll do a few of these and then set us off to working groups.
1.
That is right. There's a 1.
Yep.
There's a match of A and A. So we had 3 options. Our 3 options are this gap plus another gap. So we have -2 minus 2 is -4 coming from the left. Coming from down, we would have the exact same thing. And coming from down left on the diagonal, we have 0 plus the match or mismatch. So there are 2 different ways that we can make this calculation. It's a +1 if the characters match, A and A match. It's a -1 if the characters do not match, but they match. So we're going to take the down left value that is 0 and add 1, giving us 1. We take the maximum of these 3 values. We find that it's the 1, and we want to place a back tracing arrow to the cell that we came from. How do we do the next one? We're going to do the one right next to horizontal. Also, I brought in a new eraser, so I can stop complaining about that. Look at it. It's new. It works. Awesome.
Really amazing.
I know, right? It feels horribly cheap, but it's wonderful. All right, for the next cell, how do we calculate the value that goes here? We have those same 3 options. We have the left, we have the down, and we have the down left. From the left, what's our value?
1.
We have 1, and then we're going to take a gap penalty from there. So 1 minus 2 is -1. From the down, we have -4, -2, -6. From down left, we look at whether we have a match or a mismatch. A mismatch is G, so we're going to take the down left and subtract 1. Taking the maximum there, we get -1, and that comes from the left. Calculations make sense? Let's try to fill in the rest of this table. Work in small groups, and let's see what the optimal alignment is between Agataa and Agaga. Another fun piece of intuition as you do this is, as you start, can you think of what the optimal alignment is going to be?
No. I don't think so.
I think I know what the answer is going to be, and I think that would be it's a good piece of intuition to see if you can figure out in your mind, given these scores, what we think the alignment is going to be. Because then you can either determine that you thought something wrong, or that your intuition is good, and that can lead you and help you on a coding assignment or on an exam problem to give you a reason to double check your work.
Uh. Maybe. Maybe. Okay.
There's a good question in chat that I want to address, asking whether these initial row and this initial row and column will always be -2, -4, -6, etc. It comes from the gap penalty here, this -2. So it's going to be the row or column number times that gap penalty. So this is column 0, row 0. So you can see that as we go out, it's just multiplying the gap penalty by whichever row or column we're in.
Okay.
And you'll see in your assignment that I expect you to read in these scores from a file. So you should find the alignment based on the score, and note that the optimal alignment will change based on the scores that we have. You significantly penalize mismatches over gaps, then that can drastically change what the optimal alignment looks like.
Yep. I still got a lot more practice.
That's the score that you derived.
But I'll have you look a little closer, because I don't want you to still
Here.
class it. We're not finished, on the
Yeah,
list.
oh, gotcha, not finished yet.
Everything, just starting with. TV two. So that's fine. No, that much makes sense.
Looks like a good start.
To find your final score, you take what's in the upper right and then follow the path down and add that up.
Yeah, so the score is gonna be whatever is in this box. The path is just what's there.
Okay, so this, oh,
Yeah, the score is this value, we don't have to do anything with these other values, in fact, they all don't matter. Aside from they were used in the computation of that score, and we needed every one of those scores to calculate that score. You are. That's also a good question in chat. Why isn't there a mismatch penalty for coming from the left? We only do the mismatch penalty when we're moving diagonally.
Yeah, that makes sense.
There are two options whenever we move in that direction. Then we care about whether the two characters at this point are a match or a mismatch. If we ever come from the left or come from the down, it's always just -2 and we don't care about what the characters are.
Not sure.
Yeah. Don't need to count it. That is the actual score there. Don't touch every number leading up to that. Will be based on the similarity of the strings and the scores.
Sure, exactly.
All right, I think we probably can go over this at this point. How do we feel about these cell by cell calculations, just kind of across the class? If I could get a show of thumbs, the checking that I've been doing has involved a lot of right work, which is great. So I think hopefully I can do a couple more examples and then we can go through the optimal alignment and why that intuitively makes sense. So if we're looking at, I'm going to kind of maybe go up the diagonal a little bit. That's frequently where the answers are. The backtrace is going to say, as long as there's reasonable similarity between the strings, that we should match or mismatch, and a few gaps maybe, but not too many that will deviate from the center track. Let's do this one. How do we calculate it? What are our three options? We can come from the left. -4 minus 2 is -6 or -6. We come from down left, that's -2, and at this point we have a mismatch between the A and the G. So -2 minus 1 gives us -3, which is better than -6, best so far. We could also come from the down, 1 minus 2 for the gap penalty gives us -1, which is the best value. And that came from, yeah. Next, we can go straight up the diagonal. And again, you don't need to do this row wise or column wise. We can do it in any order that we already have the underlying portion for, the left, the down, and the down left. So in this case, we have a match. So it makes sense that rather than gapping some negative numbers, we're going to make a change to a positive number. So 1 plus 1 for the match of G and G gives us 2. That's what goes in that cell. That's going to point down left.
Yep. That checks out.
And the optimal alignment for this does in fact go straight up the diagonal. And we can see that work. This 2 is going to be a mismatch, and a match.
Yep.
On that diagonal.
We got that too.
So we should end up with a score of 1 and back tracing arrows that lead you all the way down the diagonal. And I could have gone through all of the work to prove this, but you can see this from the beginning. Notice in between these strings, there are 1, 2, 3 matches in their appropriate places at positions 1, 2, and 5 in the strings. That kind of gives us a floor for what the score is going to be. 3 matches minus 2 mismatches is going to be 1. Is there any way that starting with a gap or having a gap somewhere in there could improve on that? And the answer is yes. A single gap, in this case, could work with 1 character, then we have 4 matches. But then we would need a gap on the other end to make up for the gap that we added. So we would be taking 4 minus 4, which is 0. If we could just match the first 4 and call it a day, if they were different lengths, 4 and 5, then that would make sense. But in this case, requiring 2 gaps to get there, there's no better way to reach that 1. And that lets me shorthand a lot of this. There just is no way I could derive a score better than 1 based on the constraints of the problem. So I just like walking through my intuition or how I see the problem when I give something like this. It's one thing to know how to do it and be able to show it, but oftentimes if you can make life easier on yourself, it's worth it. Questions on this concept? Do we feel like we could do this on an exam for a similarly sized problem?
Maybe.
5 by 5 is the largest I could possibly throw on an exam. It will probably be shorter.
Actually, I have a different question that is actually a little related to this, but I actually wanted to ask. So if there are any like online tools regarding the sequence alignment stuff,
Oh yes.
is there a way we could is there like an online tool you'd recommend for us to try using to help us verify our answers to make sure we're practicing well?
I can find one, but I'm sure there will be lots, but I can recommend one.
Okay, I'm glad I asked. I've done a little bit of searching, but not much
Yeah.
because
I wanted to give people a sample input and output file as well, so that you can throw in the input file and see if it generates the output file. I have not done that yet, but that is something on my to-do list.
Okay, I guess. Well, it looks like our assignment will also help with that too.
Then the other thing is, do you feel ready to write the code for this? Do you understand kind of how this works in general? And then the next step will be translating that into code. There was a little bit of pseudocode on the slides that I will reveal ahead of your work on this so that you don't have to do absolutely everything from scratch. But implementing that pseudocode will be the next thing. And if you would like some help getting started with that, feel free to swing by office hours. I can give you a nudge in the right direction.
Now,
Any last minute questions with regards to these calculations or sequence alignment? How it maps to dynamic programming, why it's as efficient as it is? Okay. Away it goes, and I have another dynamic programming practice problem for us that has nothing to do with this algorithm.
okay,
But it does have something to do with something I enjoy thinking about on the side. Which you might not expect of a random computer science professor, but I enjoy sabermetrics, baseball statistics. So I loved finding this problem in the book, and I think it would be very fun to work on in class. So the basic idea is that we are the general manager of a baseball team. And during the off season, we need to sign some number of players that maximize the wins above replacement, the quality of player that we have, and minimize the cost of signing those players. Those are the two constraints on the problem. We want to maximize the quality of player. We want to minimize the cost of acquiring those players. So you can imagine that there is a pool of free agents, and for some reason, we get the pick. We know what they're going to sign for. There's no negotiation with other teams. There's no back and forth. There's just the cost of acquiring the player and the level of performance that they will give us. It would be nice if we knew that information in real life, but this leads to an interesting dynamic programming problem where we have a constraint that is the amount of money that we have to spend. And we can't go over that amount of money. But we want to sign the optimal subset of players that are going to give us the most performance for the money that we invest. Except that we don't want to sign more than one player at a particular position. Who needs 5 starting pitchers? We only need 1.
What I'm hearing is we're putting together a team of just pitchers.
So thinking about this problem, we basically just need to derive an algorithm that does this. This is going to be dynamic programming in practice because there are a lot of sub-problems. You can imagine taking a path like the first decision I'm going to make is I'm going to sign this shortstop. The second decision I'm going to make is I'm going to sign this first baseman. It doesn't matter if you signed the shortstop and then the first baseman, or the first baseman and then the shortstop. You end up with the same sub-problem. You've invested the same amount of money, you've acquired the same amount of wins above replacement, you have the same amount of money remaining to sign further free agents. So how do we go about that? How do we turn this from a problem that we have to brute force into a problem that we can cache and look up the solutions to when we recognize a similar subproblem? So this is meant to be an interesting exercise, but I do want people to work in groups for this. It's kind of been optional before, but I want you to find a group of between a total of 2 and 4 people, let's say. And let's see if we can work to derive an algorithm. This will be what I anticipate being the rest of class. But I want people to be able to talk about their answers that they derive, either by the end of class or potentially, depending on the work that's going on, at the start of next class. So let's get thinking. I can blow this up a little bit if it's difficult to read, but it's kind of read half and half, but it's on a line by line basis.
yeah,
No problem.
oh, I know this is an algorithm, still.
What I can do here is I can try to zoom in camera ever so slightly if I move it just a little bit. Yeah. Or How visible is this from the back in here? Yeah.
Copy of the variable. There's on the light.
What was that? Sorry?
We get a written copy of the variable on the whiteboard.
Written copy of the variables on the floor. I can do that.
That should be. Yeah, sure, I thought that should be saying int or doubles to that. Yeah. Whatever performance.
So we have X dollars. We want to maximize cumulative player performance value and minimize cost. We would rather, if there's a tie, we would rather have more performance than less cost. So maximize the performance. If there are multiple equal performances, pick the one with the less cost, lesser cost.
You may assume that each player signs for multiple $1,000. At least that's. I just,
So we can say that, yeah, it says to think about this from the performance perspective of there's a, everyone signs for a multiple of $100,000. Let's see.
multiple, eh? Yeah. Guys, algorithm. Oh, boy. These are baseball players.
Yeah, it's a big like left, right?
Oh,
As you design the algorithm, you don't need to know the positions, just assume that there is a list of players that are available that you can sort by either of these two metrics. The cost to sign them or their value.
Fascinating.
That's Jimmy.
Yeah, what a double check. It is enough players for a team or just one player per position?
We can assume that we have an entire minor league system of 0 WAR players. So we can field 0 WAR at any position.
Yeah.
So we don't need to find an entire team, we just need to upgrade from an entire team of nothing to the best of our ability.
Yeah.
Buffer makes sense.
In theory, a 0 WAR is something that costs no money, and it's something that you could freely just acquire and trade for $0 for another team. It is so valueless that another team somewhere out there has that player and will give them to you for the value of their contract. The minimum salary.
It didn't affect the cost.
Hmm?
I thought the war didn't affect the cost.
It will have a correlation. So usually better players have higher WAR, have cost more money, but there are other considerations like market inefficiencies. Decades ago, power was paid for so much more than defense. The whole Moneyball argument was average was paid for so much more than on base percentage.
Yeah, so some problem with this is we're basically have like many different positions.
War is trying to accumulate all player value into one statistic, as opposed to it being kind of all over the place with the associated market inefficiencies. So we can imagine that we are the first people to come up with this stat war, and there is a reasonable correlation, but not a perfect correlation between player valuations and like the cost and the money that it costs to sign up. We want to find the best subset of players to purchase from the free agent market that will
Play with a little more and also a higher.
could be. In which case, they're probably not part of the solution. But it could be that you have to choose between spending more on one position for significantly more war, or splitting that among 2 players or among 4 players. Because we have 4 players add up to be the cost of 1 player.
I feel like, this is something I haven't thought over in a while, but I was thinking of using a struct or something. But it's like, is an interpretation for this type of problem? Because we got 3.
So you don't need to worry about how the data is being stored. If you're thinking about using like what kind of structures would you use, that will be independent from the operational algorithm of how do we select players. You could think of something like we instantiate a list that is going to be the players that we choose to hire. We're going to think about filling the list with how do we make those decisions.
Well, okay. Oh, wait. And number of positions. All right. Yeah, I'm kind of slow on this one right now. Trying to think through everything.
Yeah.
Where it starts. Got the base value. That's a lot of options.
There already associated cost if you don't sign a player.
There's no cost. We're gonna promote someone from the minor league system that has 0 WAR. So we can fill the position, no problem. It just won't contribute to our win total beyond a base level of Usually, the calculation is if you fill an entire field full of 0 war players, you would have 43 games and 150 games. At least that was a historic. I don't know if that's still, but that's not a good performance. But you could sign 1 star player for all of your money if that is the best use of your resources, and then just have kind of a stars and scrubs kind of lineup, like the Angels had with Mike Trout in the 20 teens. Absolute stars surrounded him with nobodies, so that when he got hurt, the team didn't perform. But you could carry the whole team sometimes.
Yeah, so higher war value, more value.
That's why I think.
Yeah, I get the point. I'm not entirely sure myself either. Because it's like a whole precedence.
Now I need to see it.
Some player, how much more, how much more. So player.
I have a lot of right ideas, maybe.
Base you want to use for this is similar to something we've seen before.
Yeah, it's like a recording. So. Well, make a base case with how it would be total cost. So.
Right, I'll give people that hint at this point. You've seen this before. Almost exactly this problem. What is it and where have we seen it?
2 seconds ago.
Right idea, but no.
How does this map onto the rod cutting problem?
Oh yeah, this is like, we broke it apart trying to find the best cost of cutting it into as many pieces as we did.
So in this case, rod length, you're given that at the beginning, like here's the
Yes.
amount of steel we have to work with. That is the amount of money that you have to work with, that is X. We figured out, all right, well, why start focusing on X dollars when we can come up with a baseline? We're going to build from the bottom up. What is the best way to break down and have a rod of length 1, rod of length 2 based on a rod of length 1, rod of length 3 based on a rod of length 2 and 1, rod of length 4 based on 3 and 2 and 1. We can do something very similar here with money. You can find the best team you could field with $100,000. Given that, what's the best team you could field with $200,000? You could either break it down into the best team you could field with $100,000 plus an extra $100,000, or a single player with $200,000. Given that breakdown, you could look at $300,000. build from the bottom up. Given that, let's hone our focus and come up with the algorithm. What's different between the rod cutting problem and this problem? And given that we could solve the rod cutting problem, how could we solve this problem?
Yeah,
That was basically the cost of that length, right? There was a profit, that's something we can sell that for. That sale price is going to be our value. Yeah, that is a great point in chat. We have the different positions. And if we've already signed one position, we can't sign another good player out of that position. So there may be some additional work that we need to do to figure out, do we pivot to another player in that position group to save money? And does that unlock the ability to better optimize? So there's a bit of an extra dimension to this. Got like quiet in the classroom, dead silent.
right. Yeah, that is true. We usually will struggle with all of that. We will also figure out like the most optimal way to cut it for this.
But if we're having one more thing, then I'm every quarter.
Okay. Another idea. So, whoa, time has gone by so fast.
So are we thinking that we need to iterate through to check every dollar amount to see what player we decide?
I would build this based on dollar amounts. I would have nothing to do with sorting the players by their war or trying to focus on which position should I think about first. Build this in terms of money from the ground up. Because if we have X dollars, then if we had X minus $100,000 and we solved that problem, we could then ask the question, how do we best utilize that last $100,000? Do we add that $100,000 to any sub-problem? And we could now look at that in terms of, we'd already have solved those sub-problems in some other situation based on the exact breakdown of the amount of money we have. So let's say we have $1 million, just 10 of these $100,000 increments. So we'd have, by the time we're asking a question about $1 million, we've solved the $900,000 question. We know how to optimize and fully field a team with $900,000. We can either take that answer and add the best that we can do with $100,000 from there. Or we could take the best team that we could fill with $800,000 and add $200,000 to that. We did have a sub-problem of $200,000. We just have to find the overlap between the players in the $800,000 and the players in the $200,000 and try to then re-optimize, given that we can't hire two of the same player. Or we could look at the best team we could field with $700,000 and try to add $300,000 to that. So mesh the $700,000 team with the $300,000 team, dealing with any overlaps.
Wondering about the 100,000 first, like, why does that matter? But
Yeah, that is why that matters. And here is, it grounds you a little bit in the problem. You'll find this is a very common kind of interview question. And this is a great, when we do talk about interviewing eventually, you can find a lot of hints to how to solve problems like this embedded in the questions. If you were tasked to solve something like this in an interview, why is the $100,000 there? If you're wondering that question, That's a great gut check for, this is relevant somehow. How or why is this relevant? It's part of the solution. If we had to build up teams for every $1 increment, this would take a little while. Few minutes left. What have we come to the conclusions of? Anyone want to share their group's work? Since we've gotten the hint, kind of what would we do to optimize this problem? How would we deal with the overlaps in players? I can give people my thought process on this. So if we're building up that table, what I'm imagining is, let's say, I'll give you an example of, we have that $1 million. We're looking at the sub-problem as we're trying to build up the optimal $1 million. We're looking at a breakdown of $700,000 and $300,000. So there's the optimal 700 problem that we've solved. There's the optimal 300 that we've solved. Let's say there's some overlap. I would imagine that each of these is going to be a lookup. There is some number of players that make up each of these teams, but imagine that there is a similarity between those. Do we want to try to recalc the 300 saying this player doesn't exist? That would be building up from 100 to 200 to 300, taking that player out of the player pool. That would be something that we could do and say, what is the best $300 team that we can field without that player? And then if we found that that involved another overlap, then we'd have to start over, remove that player from the pool. So you could do that. Be worth analyzing what the complexity of that problem would be in the worst case. Alternatively, yeah.
You can break it down into then 700, 200, 100, and then see the 100s.
Yeah. So like what combinations can we use to break in the 300s if that player doesn't exist? What is the best breakdown of lookup problems that bring up 300 that doesn't involve that player? Or doesn't involve any player in this list? Would we have stored all of those problems as we went?
If we wanted to.
Yeah, we could. We could build up for every player, we could remove one player or subsets of players and try to derive the best combinations. How many combinations are there going to be as we build up this table? Unfortunately, there'll be an exponential number of combinations, so we can't fully solve that problem efficiently, but it's a great idea. I'll let people think about this between today and tomorrow. How would you break this down? We can come back to this and kind of talk about it a little bit more as a group because we are out of time. But we're going to move on to greedy algorithms after this, and we're going to talk about what happens when you can make interesting assumptions about problems that lead to optimal solutions being easier than a brute force solution. So that's what we have to look forward to tomorrow.
All right. Well, it is at least something. I'm not really finding it right now, but I didn't take as many notes.